This lesson deals with a node voltage example with current sources. You can find these notes in the course ebook in Chapter 3 starting on page 3. In this example, I have 2 current sources and 3 resistances. And could you find the voltage across and the current through every element in this circuit? In this problem, there are 3 nodes, here, here, and here, and thus there are 2 unknown node voltages. If I can find those node voltages, I can solve for any voltage or current. I'm going to do this in a 5-step algorithm. The first step is to select the reference node if you need to. In this problem, 1 wasn't indicated, so I'm going to pick the one on the bottom, use the ground symbol, and what this means is that there's 0 volts here. Step 2 is to define the node voltages if you need to. In this case, they weren't specified. I'll call this node number 1, and this node number 2, although you can call them anything you want to, as long as once you do that, you stay with it. Step 3 is to apply Kirchhoff's current law at each non-grounded node, expressing each resistor current in terms of the unknown node voltages. Now, since node voltage 1 is from node 1 to ground, plus to minus, then the current would be in the direction from the plus to the minus terminal, using Ohm's law. The same is true for the 1K resistor here, where I've got V2 volts from 2 node to ground, and the current would then flow from the plus to the minus terminal. Now, the current in element 3, I could pick arbitrarily in this direction or this direction. If I pick it in this direction and get a value, the current in the opposite direction, had I picked that, would be the same magnitude but the opposite sign. So we'll arbitrarily pick some currents, others will be defined by Ohm's law. And again, the node voltages V1 and V2 can be positive or negative. So let's do Kirchhoff's current law at node 1. The current that enters the node equals the current that leaves the node. 3 milliamps is entering, I1 is leaving, and I3 is leaving. But what's I1? It's V1, the node voltage V1, divided by 1K. What's the current in the 3K resistor? With this direction of current, we're implying a voltage in this direction. By Ohm's law, it's going to be node voltage 1 minus node voltage 2 divided by 3000. Let's put all the things that multiply V1 together and V2 together. I have V1 over 1K, V1 over 3K, and then I have a minus 1 over 3K times V2. So here I have one equation and 2 unknowns, V1 and V2. To solve this, I need another equation. We'll do that at node 2. The current that enters the node is I3. The current that leaves is I2 and 5 milliamps. Let's solve for this equation. I know 5 milliamps, and I'll bring the I2 on the other side of the equation, so I get I3 minus I2. What's I3? V1 minus V2 divided by 3K. And what's I2? It's going to be equal to V2 divided by 1K. Let's group the things that multiply V1 together and V2 together. V1 is multiplied by 1 over 3K. V2, though, is multiplied by 1 over 3K with a minus sign, and also V2 over 1K with a minus sign. Bring those minus signs out and have the addition of these 2 terms. I have a second equation in the 2 unknowns V1 and V2. Step 4 is to solve for the unknown node voltages. From our first equation, we have 3 milli is equal to 1 over 1K plus 1 over 3K. 1 over 1K is 1 milli. 1 over 3K is 0.33 milli. 1.33 milli times V1. And then we had a minus 1 over 3K. And 1 over 3K is 0.333 milli. And that multiplied V2. The second equation, we had that 5 milli was equal to 1 over 3K times V1, 0.33 milli, minus the summation of 1 over 3K plus 1 over 1K, and that again is 1.333 milli, but there was a minus sign with the V2. You can put this into matrix notation, just a shorthand notation for this equation. That 3 milli is equal to 1.33 milli times V1 minus 0.333 milli times V2. The second equation is that 5 milli is 0.333 milli times V1 minus 1.33 milli times V2. There are inspection techniques in linear algebra for solving for V1 and V2. One of these such methods is called Cramer's rule. If I want to solve for the voltage V1, and this is really associated with column 1, because we're going to multiply this times V1 when we say the first equation, and the second equation, same thing, this times V1. Take this matrix and replace the first column by the column we're solving for, which is V1, with the left-hand side of the equation. My 3 milli and 5 milli, and my other 2 entries are here. I'm going to find that determinant. And it's divided by the determinant of the original matrix. On a test, I won't give you bigger than a 2 by 2 matrix. If you recall from algebra, to find this determinant, do a cross multiplication, 3 milli times a minus 1.33 milli, minus 5 milli times a minus 0.33 milli. It's this times this, minus this times this, just a cross multiplication. Same is true for the denominator determinant, 1.33 milli times a minus 1.33 milli. and then minus the product of these two, which should be 0.33 milli times a minus 0.33 milli. If you multiply this out, this is minus 4 micro. If you multiply this out, it's 1.667 micro. This is 1.778 micro, but a minus sign. And this two minus signs cancel, and I get 0.111 micro. Adding these terms together, you get a minus 2.33 micro divided by 1.667 micro. That turns out to be 1.4 volts. So I now have node voltage 1. If I want to solve for node voltage 2, we'll do a similar process. So column 2 was associated with V2. Take the original matrix, replace column 2 by the left-hand side of the equation, and find that determinant divided by the original determinant. So again, cross-multiplying 1.33 milli times 5 milli minus 0.33 milli times 3 milli. Our denominator determinant we already found is a minus 1.667 micro. Multiplying this out, I get 6.667 micro, and here I get 1 micro because of the minus sign, still minus sign there. And that gives me a minus 3.4 volts. Again, node voltages can be positive or they can be negative, but now that I know those, I can find every other variable in the circuit. And step 5 is to complete the problem. So I know node voltage 1 is 1.4 volts. I'm just going to write that onto the drawing. And that node voltage 2 is minus 3.4 volts. The current I1 by Ohm's law is just going to be 1.4 volts divided by 1K, and that's 1.4 milliamps. The current I2 in this direction is going to be the voltage divided by the resistance, and that's going to be also negative, minus 3.4 milliamps. The node voltage 3 I defined from node 1 to node 2. It's going to be the value of 1.4 volts minus a minus 3.4, and that gives me 4.8. And then the current that I've picked because of the polarity of voltage by Ohm's law would be 4.8 volts divided by 3K, and that's 1.6 milliamps. And this is an example using node voltage techniques with current sources.